Human history is littered with stories of experiments that pushed beyond the boundaries of understanding, daring to probe forces only barely grasped. From alchemists mixing volatile potions in candlelit chambers to physicists splitting the atom in secret laboratories, curiosity has always been a double-edged sword. Each breakthrough has offered new light but also cast new shadows. For when we tamper with the fundamental architecture of nature, we are not merely observers, we are participants, and participation always carries risk. In the modern age, nowhere is this tension sharper than at CERN, the European Organization for Nuclear Research. Buried beneath the Franco-Swiss border lies the Large Hadron Collider, a ring 27 kilometers long, where protons are hurled at nearly the speed of light before smashing into one another with energies unseen since the birth of the universe. It is here that the ATLAS experiment, the largest particle detector ever built, stands as both cathedral and crucible, designed to catch the fleeting whispers of fundamental particles. ATLAS has already etched its name into history by helping confirm the Higgs boson, the elusive particle once dubbed the God particle. That triumph was not only a validation of decades of theory, but also a testament to humanity's audacity. We reached into the void and plucked from it a truth about existence itself. Yet, even as champagne corks flew, a quieter question lingered. In the background, what else might we awaken? For every discovery at the edges of physics, there is a corridor of uncertainty stretching further than we can see. Some corridors lead to progress, new technologies, deeper understanding, unexpected cures. Others may lead to walls, blind alleys where nature offers no further passage. But the darkest possibility is that one corridor leads to catastrophe, that in probing the unknown, we stumble upon forces beyond our control. This is the unsettling stage upon which the concept of 3I emerges. Within ATLAS and the labyrinth of theories surrounding it, 3I is whispered about as a convergence point, 3 instabilities intertwined, 3 infinities intersecting, 3 impossibilities colliding. Its meaning is opaque, part theoretical, speculation, part ominous metaphor. Some frame it as a threshold where equations collapse, others as a shorthand for scenarios that defy comprehension. What is clear is that 3I represents the kind of boundary that physics both craves and fears, the place where knowledge turns into danger. The story of science has always been the story of Pandora's box. Each time we pry open the lid of nature, wonders spill forth, but so too do hazards. When fire was first tamed, it warmed homes and cooked meals, yet it also burned villages to ash. When nuclear fission was mastered, it illuminated cities and annihilated them in equal measure. And now, with machines like ATLAS, we pry at the seams of reality itself. Might the next revelation bring insight or peril? It is not alarmist to ask. Before the Large Hadron Collider was switched on in 2008, critics worried that it might create microscopic black holes or trigger runaway reactions. Physicists assured the world such scenarios were vanishingly unlikely, pointing to natural cosmic rays that strike Earth with far greater energy. Yet, the public unease revealed something deeper. We are entering a realm where the consequences of our curiosity are no longer intuitive. When the subject is the structure of space-time itself, the risks are cosmic in scale. The contrast is cinematic. On one side stands human curiosity, the drive that built cathedrals, mapped genomes, split atoms, and sent probes beyond the solar system. On the other side looms cosmic peril, the possibility that curiosity, unchecked, could unravel the very stage on which we stand. ATLAS, in this framing, is both triumph and Pandora's box, symbol of how far we have come and reminder of how fragile our place may be. And yet curiosity is not optional. To be human is to ask, to seek, to risk. The ominous question, what could go wrong, is not meant to paralyze but to sharpen awareness. It forces us to confront the stakes honestly, to balance ambition with humility. The existence of concepts like 3I is not a prophecy of doom, but a signpost. There are thresholds in physics we do not yet understand, and approaching them requires vigilance as much as vision. Consider the irony, the very machines that may expose. Hidden dangers are also our best defense against them. Atlas does not blindly pry at the universe. It observes with extraordinary precision, seeking to understand the laws that govern risk itself. In probing 3I, scientists are not reckless gamblers but cautious navigators, aware of the abyss, yet compelled to map its edges. The peril lies not in asking but in failing to prepare for the answers. This is the story that will carry us forward, a narrative poised between wonder and dread. If Atlas uncovers deeper instabilities, whether 3I proves to be a mathematical curiosity or a doorway into new physics, it will remind us that knowledge and danger are often two faces of the same coin. Human progress has always been forged in that tension, in the willingness to face ominous questions without flinching. The opening of Pandora's box was not the end of the story, but the beginning of hope. So too with Atlas, in daring to ask what could go wrong, we also discover what could go right. Perhaps the mysteries we fear will turn out to be opportunities, new realms of discovery that reshape existence without destroying it. Perhaps the very act of confronting cosmic peril will deepen our resilience as a species, but the haunting question will never vanish. Every collision within Atlas, every whisper of instability, every hint of 3I reminds us that we are not only explorers but gamblers, wagering with stakes as vast as the cosmos. What could go wrong? Everything. What could go right? Perhaps more than we can yet imagine. Atlas, humanity's giant eye on the universe. If the Large Hadron Collider is a colossal engine of discovery, then Atlas is its unblinking eye, the instrument that gazes into the smallest fragments of creation and translates their fleeting whispers into knowledge. Few machines in human history embody both awe and intimidation so completely. It is a device as large as a cathedral, yet built not for worship but for interrogation, a chamber where the universe is compelled to reveal its secrets, particle by particle. The Atlas detector is almost incomprehensible in scale. Standing 25 meters tall, stretching 46 meters long, and weighing more than 7,000 tons, it occupies a cavern buried deep underground. To enter its chamber is to walk into a technological cathedral, vast steel ribs, layers of sensors stacked like stained glass windows, magnetic coils arching like flying buttresses. Its architecture is less Gothic than futuristic, but the metaphor holds that the machine inspires reverence, not only for its size, but for the ambition it represents. At its core, Atlas is designed to do something almost mystical, to observe events that last less than a trillionth of a second. When protons collide inside the collider, they create showers of particles that explode outward like sparks from an anvil. Most vanish instantly, leaving only faint traces of energy and momentum. Atlas captures these traces through concentric layers of detectors, pixel sensors closest to the collision, calorimeters measuring energy, and muon chambers at the outermost edge, tracking ghost-like particles that slip through everything else. Each layer is a guardian of information, reconstructing collisions as if reassembling shattered glass back into its original shape. This eye does not blink. Every second, the collider produces up to 1 billion collisions, and Atlas sifts through the chaos with ruthless selectivity. Sophisticated trigger systems decide in microseconds which events are worth saving, discarding the rest. In its vast data vaults lie not just the collisions themselves, but humanity's attempt to glimpse truths written into the foundations of matter. Atlas is both witness and judge, deciding which fragments of reality are preserved and which vanish into oblivion. The machine's triumph came in 2012, when Atlas, alongside its sibling experiment CMS, announced the discovery of the Higgs boson. For decades, the Higgs had existed only as an idea, a missing cornerstone of the Standard Model. Without it, the mathematics describing the zoo of particles would collapse. Physicists often called it the God particle, though the name was more journalistic flair than theological claim. Still, the discovery carried the weight of revelation. Atlas had done what no eye before it could do. It had glimpsed the particle responsible for giving mass to matter, the invisible mechanism that allows stars, planets, and people to exist at all. That discovery was not just science, it was spectacle. Around the world, physicists wept in lecture halls as the data appeared. Headlines announced a triumph of reason, the moment when one of humanity's most ambitious machines fulfilled its promise. Atlas had peered into the void and found not chaos but order, not silence but a hidden note in the cosmic symphony. For a moment, the cathedral fulfilled its purpose, lifting the curtain on creation. And yet, for all its grandeur, Atlas also provokes unease. Its scale, its power, its ability to probe energies unseen since the first instance after the Big Bang. It intimidates as much as it inspires. When critics ask whether such machines could trigger disasters, it is Atlas they picture, the enormous eye staring unflinchingly at forces no human should disturb. To some, it is not a cathedral of knowledge but a collider of nightmares, a reminder that our ambition can summon powers we barely understand. This contrast is sharpened by the machine's very location. Buried underground, sealed in caverns, it evokes imagery of ancient rituals carried out in hidden temples. Only here, the rituals are collisions, and the sacrifices are protons hurled at each other with unimaginable violence. To walk the halls of Atlas is to sense both the wonder of human achievement and the chill of hubris. We have built a machine to recreate the fires of creation, to summon echoes of the Big Bang itself, and we trust that the cage will hold. Still, the vision is irresistible. Atlas represents humanity at its boldest. Thousands of scientists from dozens of nations, united not by politics but by curiosity. Its construction required technologies that did not yet exist, engineering feats at the edge of possibility. Like the cathedrals of medieval Europe, it is the work of generations, a structure that embodies the collective faith of its builders, not in God but in knowledge. It is a monument not of stone but of silicon, magnets and code, erected to honor the belief that truth can be uncovered through experiment. Yet unlike cathedrals, which offer sanctuary, Atlas offers no comfort. Its revelations are often unsettling. Each discovery peels back a layer of reality, exposing mysteries deeper than before. The Higgs boson, for example, while confirmed, leaves unanswered questions about why its mass is what it is, or whether it hides connections to unknown realms of physics. Atlas does not provide closure, it expands the frontier, beckoning us toward even darker corridors. In this sense, Atlas is both a beacon and a warning. It shows us what humanity can achieve when curiosity triumphs over fear. But it also reminds us that each answer brings new risks, that knowledge and peril are twin siblings. The Cathedral of Knowledge is also a collider of nightmares, and we cannot separate one from the other. So we stand before Atlas with mixed emotions, awe at its power, reverence for its discoveries, and unease at the dangers it represents. It is a machine that reflects us back to ourselves magnified. We are brilliant, ambitious, united by curiosity. We are also reckless, fragile, tempted by forces that may exceed our grasp. Atlas is our mirror, showing both the heights of our triumphs and the shadows of our fears. The great question lingers: what comes next? Atlas continues to operate, gathering data, probing deeper, searching for cracks in the standard model, hints of dark matter, whispers of dimensions beyond our own. Each collision could be ordinary or extraordinary. The eye watches and humanity waits. Every cathedral of knowledge casts a shadow, and within the halls of Atlas that shadow has a name whispered with unease: 3i. At first glance it seems an innocent shorthand, a cryptic label buried in conference slides and speculative papers. But behind those two characters lie three specters that haunt modern physics: instabilities, intersections, and infinities. Together they form an enigma at the edge of theory, mathematical, elegant, and terrifying. What does 3i mean? At its core, it points to three different kinds of danger that emerge when equations push past the safety of what is tested and known. The first is the possibility of instability in the vacuum itself. The second, is the intersection of forces, when the universe's most fundamental interactions converge in ways we may not be prepared to contain. The third is the problem of infinities calculations that spiral into runaway values, hinting not only at broken mathematics but at catastrophic physics. Each of these alone is troubling. Taken together, they sketch a portrait of a cosmos balanced on the edge of peril, instability, a precarious vacuum. Physics begins with a startling assumption that the vacuum, empty space itself, is stable. Yet quantum theory suggests that the vacuum may not be empty at all, but rather a seething field of energy, restless and dynamic. The Higgs boson discovery, triumphant though it was, sharpened this fear. Calculations based on the Higgs mass suggest that our universe might be perched precariously in a metastable state, stable for now, but not forever. If true, then space itself is like a glass resting on the edge of a table, balanced but vulnerable. A catastrophic event, perhaps triggered by an ultra-high energy collision, could nudge it over the edge. The vacuum could decay, rolling down to a lower energy state, unleashing a bubble of destruction that expands at nearly the speed of light, erasing everything in its path. Galaxies, stars, atoms, obliterated not by explosion, but by redefinition, rewritten into a new reality where our physics no longer applies. Most physicists stress that such a scenario is vanishingly improbable, especially given that cosmic rays strike Earth's atmosphere with energies far beyond anything we generate in accelerators. But improbability is not impossibility, and when the stakes are cosmic annihilation, even whispers of risk echo loudly. This is the first I, instability, the fear that our vacuum is not as eternal as it seems. Intersection, the forces converge. Second spectre arises from the dream of unity. Physics seeks simplicity, an ultimate equation that explains gravity, electromagnetism, the strong force, and the weak force as facets of a single principle. This search for a grand unification is one of science's most noble quests. Yet unity can also be perilous. When forces intersect at extreme energies, their distinctions blur. The equations of grand unification predict that under certain conditions, particles could transmute, symmetries could collapse, and phenomena hidden since the dawn of the cosmos could erupt anew. Such intersections might reveal pathways to entirely new physics, but they might also awaken processes that destabilize matter itself. In speculative nightmares, the unification of forces could allow proton decay on catastrophic scales, unraveling the very fabric of matter. Or it might open channels for exotic particles to flood existence, disrupting the balance of forces that holds stars and planets together. In pursuing the dream of elegance, one equation, to bind them all, we risk stirring dynamics that belong not to human laboratories, but to the furnaces of the Big Bang, thus the second I, intersection. The crossroads of fundamental forces is both a temple of elegance and a potential minefield of dangers, a place where the equations we write in chalk might manifest as forces beyond our control. Infinity, the runaway abyss. The third danger is subtler, but no less chilling. Infinities emerge when calculations spiral out of control, producing results that defy physical meaning. The equations of quantum field theory are littered with these runaway terms, threatening to assign infinite mass or energy to particles. Physicists tame them with techniques like renormalization, trimming away the absurd values to leave behind predictions that match experiment. But renormalization, ingenious though it is, feels like a patch rather than a cure. It works beautifully, reliably, but it also hints that we do not yet truly understand what lies beneath. And when infinities arise in attempts to merge quantum mechanics with gravity, they resist all efforts at cancellation. A black hole's singularity, for example, is not merely a mathematical curiosity, but a gaping wound in theory, where infinities tear through our equations like cracks in glass. The nightmare is not only mathematical, If infinities represent actual features of nature densities, curvatures, or energies without bound, then they may correspond to catastrophes of reality itself. The abyss in math might be an abyss in the cosmos, a place where even our categories of existence collapse. Thus the third I, infinities, the spectre of runaway values that refuse to be tamed, reminding us that our models may be fragile scaffolds clinging to a deeper truth we cannot yet articulate. Elegance versus catastrophe. Taken together, 3I is not a single prediction but a mood, a cipher for how close the border between beauty and terror truly lies. Theories that dazzle with elegance also harbor seeds of disaster. The Higgs boson's precise mass, a triumph of measurement, becomes a whisper of vacuum instability. The dream of unification, elegant and symmetric, becomes a reminder that convergence may unleash dynamics we cannot reverse. The mathematics of infinities, intricate and ingenious, becomes a warning that our language itself may break under pressure. This duality is what makes 3I so unsettling. It is not pseudoscience, not fantasy. Each of its components is rooted in serious debate, respected equations, and rigorous speculation. Yet together, they blur the line between scientific rigor and terrifying speculation. They remind us that the further we reach into the unknown, the closer we come to thresholds where possibility shades into peril. Atlas, in this framing, is not just an instrument of discovery, but also a participant in this drama. Every collision it records, every trace it deciphers, nudges us closer to the domains where 3I lurks. Will we find reassurance that the vacuum is stable, that unification is benign, that infinities are illusions of our limited models? Or will we uncover hints that the risks are real, that our universe rests on foundations more fragile than we dared to imagine? How should we confront 3I? With fear or with courage? The answer may be both. Fear keeps us cautious, demanding rigor, peer review, and safeguards. Courage propels us forward, daring to ask questions even when answers could unsettle. Human curiosity has always thrived in this tension. The same impulse that split the atom also unlocked nuclear medicine. The same drive that harnessed electricity also risked electrocution. Progress has always walked hand in hand with peril. The enigma of 3I is a reminder that science is not a march toward certainty, but a dance with uncertainty. It forces us to admit that our most elegant mathematics may conceal catastrophic risks. Yet, it also shows that acknowledging danger is itself a form of wisdom, a sign that we are awake to the stakes of our explorations. The Cathedral of Knowledge casts shadows not to frighten us away, but to remind us of the scale of our quest. 3I is both enigma and omen, a shorthand for the fragility of existence and the audacity of human inquiry. It is the reminder that beneath every elegant equation may lurk a catastrophe, and that to explore the universe is to accept that risk. Vacuum, decay, the ultimate chain reaction. There are few scenarios in physics more chilling than the possibility that the ground beneath reality is not solid at all, but precariously balanced like a glass on the edge of a table, waiting for the smallest nudge to send it crashing down. This is the spectre of vacuum decay, the idea that the very fabric of space could collapse into a lower energy state, rewriting the universe in an instant. To understand this dread, we must return to the Higgs field, the invisible energy field. Discovered through the Higgs boson at CERN in 2012, the Higgs field is what gives particles their mass. Without it, atoms, stars, and life itself could not exist. For decades, physicists assumed it sat comfortably at the lowest possible energy, like a ball resting at the bottom of a valley. But when the Higgs boson's mass was measured, the numbers told a different, unsettling story. The Higgs field might not be in the valley's lowest floor at all. It might be perched on a higher ledge, metastable, balanced, but not final. If this is true, then the universe is not resting in a true vacuum, but in a false vacuum, a temporary state of stability. And metastability always carries risk. Given the right trigger a rare quantum fluctuation, or perhaps a sufficiently energetic event the Higgs field could tunnel into a lower energy state. This transition would not be gradual, it would be a catastrophic phase change, like supercooled water suddenly crystallizing into ice. A bubble of true vacuum would form, then expand outward at nearly the speed of light, consuming everything in its path. The consequences defy imagination. Within the bubble, the laws of physics themselves would be rewritten, the strengths of forces could change, the masses of particles could vanish or inflate, atoms as we know them might not survive, chemistry itself could become impossible. The universe would not burn or explode, it would be redefined, and because the bubble expands at light speed, no warning would ever arrive. One instant we are here, the next instant we are gone, absorbed into a cosmos governed by alien rules. This scenario sounds like science fiction horror, but it emerges naturally from the mathematics of quantum field theory. When physicists plot the Higgs potential, the landscape of possible energy states, the measured Higgs mass places us perilously close to the border between stability and instability. We may live in a safe valley or on a plateau, destined eventually to collapse. The cinematic dread here is obvious. Imagine the universe as a candle flame, steady but fragile, with the possibility of being snuffed out without notice. Imagine every galaxy, every star, every life extinguished not by time or entropy but by a quantum twitch. Vacuum decay is not an apocalypse we could see coming or defend against. It is the most absolute chain reaction imaginable, swallowing reality itself, and yet probability tempers dread. Even if the Higgs field is metastable, the timescale for decay may be unimaginably vast, longer than the current age of the universe, by factors beyond comprehension. In cosmic terms, it may as well be eternal. Nature has endured for 13.8 billion years without collapse, weathering cosmic rays of energies far exceeding anything humanity produces. If such collisions could trigger vacuum decay, it seems likely they would have already done so. The very fact that we are here may be the universe's reassurance that the danger, though real in principle, is negligible in practice. This tension defines the drama, quantum possibility versus cosmic fragility. On one side, equations whisper that collapse could occur, that the very foundation of being is precarious. On the other, probability offers comfort, suggesting that fragility does not equal imminence. The risk is not a countdown ticking toward doom, but a faint possibility woven into the quantum fabric of existence. Still, the very possibility reshapes how we see ourselves. If the vacuum is metastable, then all of history, every civilization, every dream is contingent. We live not on bedrock but on a provisional platform, a reality that might someday give way. The fragility humbles us, reminding us that permanence is illusion, and that even the laws of physics may not be eternal. For physicists, vacuum decay is less a prophecy than a probe. It challenges our theories, forcing us to refine models of the Higgs field, to test the stability of the standard model, to search for new physics that might secure the vacuum against collapse. Supersymmetry, for instance, once promised to stabilize the Higgs potential, but so far has eluded detection. The vacuum instability problem is thus not just existential dread, but also an engine of scientific progress, driving inquiry into what lies beyond the standard model. For philosophers, it is a parable. Vacuum decay dramatizes the precariousness of existence, the unsettling fact that everything we know could vanish without warning. It embodies the contrast between our desire for permanence and the universe's indifference. It forces us to ask whether meaning requires eternity or whether fragility itself gives meaning to the fleeting span we are granted. For storytellers, it is a haunting image, a silent, invisible wave racing through space, rewriting everything behind it. Unlike meteors or supernovae, vacuum decay offers no spectacle, only erasure. Its horror lies in its silence, its inevitability, its refusal to offer any possibility of escape. In this way, it is less a doomsday scenario than an existential mirror reflecting the fragility of life itself. And yet, in that fragility, there is also beauty. The improbability of collapse means that we may live billions, trillions, even quadrillions of years before such a fate. The very fact that we can contemplate vacuum decay is evidence of how stable our cosmos has been, how long it has nurtured stars and galaxies, and how generously it has allowed life to emerge. Fragility need not imply despair. It can also inspire gratitude. The lesson of vacuum decay, then, is not to cower in fear, but to marvel at the improbable stability of our universe. The possibility of collapse is real, but so too is the evidence of endurance. We live in a cosmos balanced between possibility and protection, fragile yet lasting, a reminder that even in the face of ultimate chain reactions, life can flourish. Mini black holes, harmless sparks, or endless hunger. Few ideas have captured the public imagination and public fear like the possibility of miniature black holes forming in particle colliders. When the Large Hadron Collider was first powered up, headlines blared warnings of an apocalypse. A black hole born beneath the Franco-Swiss border, growing unstoppably until it swallowed the Earth. Lawsuits were filed. Protests erupted. Scientists reassured the public, but the haunting image remained. A tiny spark of infinite gravity, hidden in the heart of a machine, feeding endlessly on the matter around it. The reality, according to theory, is more subtle and more reassuring. In principle, colliders like the LHC could produce microscopic black holes if extra dimensions exist beyond our familiar four. These dimensions, predicted by speculative extensions of string theory, might lower the threshold for black hole formation, making them possible at energies accessible to us. Yet if they do appear, they would not be cosmic predators. They would evaporate almost instantly through a process known as Hawking radiation. Proposed by Stephen Hawking in 1974, this mechanism arises from quantum effects near a black hole's event horizon. Pairs of particles flicker into existence from the vacuum. Normally they annihilate and vanish, but near the horizon, one particle can fall in while the other escapes. To a distant observer, the black hole seems to emit radiation, slowly losing mass until it evaporates entirely. For a mini black hole, this evaporation would occur in less than a trillionth of a second, far faster than it could consume even a single atom of its surroundings. Instead of a growing monster, a collider black hole would be a harmless spark, vanishing almost as soon as it appeared. This is the safety assurance physicists emphasize. Nature itself provides the precedent. Cosmic rays, high-energy particles from space strike Earth's atmosphere with energies far greater than those inside the LHC, and they have been doing so for billions of years. If mini black holes could persist, Earth and countless other planets and stars would have been devoured long ago. The absence of such catastrophe is empirical evidence that collider-born black holes pose no danger. The cosmos, in this argument, has already run the experiment trillions of times and rendered its verdict safe. And yet, speculation thrives in the gaps. Hawking radiation, elegant though it is, has never been directly observed. It remains a theoretical prediction, widely accepted but unconfirmed. What if it fails? What if the mechanism works differently than expected or not at all? In that case, a mini black hole created in a collider might not evaporate. Instead, it could linger, tiny and dense, drifting through matter. The apocalyptic scenario unfolds like this. The black hole settles into the Earth's core, feeding slowly but inexorably. At first, the process is imperceptible, hidden beneath our feet, but as it consumes atoms, it grows denser, hungrier. Over thousands, perhaps millions of years, it expands, devouring the planet from within. Earth would not explode, but collapse. Compacted into a sphere of searing gravity, humanity's cradle would become its tomb. Physicists counter these fears with calculations. Even if Hawking radiation were absent, the probability of such black holes being trapped by Earth is exceedingly small. Their tiny size and immense speed would allow them to pass through matter like ghosts, slipping out into space before they could consume anything. Moreover, astrophysical evidence provides further reassurance. White dwarfs and neutron stars, incredibly dense objects bombarded by cosmic rays, remain intact. If stable mini-black holes could form and grow, such stars would have been destroyed long ago. Still, the very need for reassurance reveals the tension at play. On one side stand the safety assurances grounded in theory, observation, and logic. On the other side loom the apocalyptic what-ifs, fueled by the possibility that even a small gap in understanding could unleash catastrophe. The contrast is not between reason and irrationality, but between two perspectives, one emphasizing probability and precedent, the other haunted by the stakes of being wrong. This tension is amplified by psychology. Black holes, more than any other astrophysical object, embody fear. They are the monsters of the cosmos, devouring light, bending time, swallowing entire stars. To imagine one born in a laboratory is to fuse our deepest awe with our darkest dread. Even if the science says otherwise, the image is too potent to ignore. A cosmic predator unleashed by human hand, a nightmare in the basement of Europe. For scientists, the challenge is communication. They must explain that black holes are not inherently destructive. Their danger comes from scale. A black hole with the mass of the Earth could consume worlds, but a black hole with the mass of a proton is harmless, evaporating instantly. The analogy is like comparing a spark to a wildfire. The physics is the same, but the scale determines the outcome. Yet in the public imagination, scale blurs, and the word black hole overwhelms nuance. There is also irony here. If mini black holes were produced far from being a threat, they would be a revelation, a sign that extra dimensions exist, that gravity behaves in ways we never anticipated, that new physics lies within reach. Their evaporation could provide evidence for theories that have remained speculative for decades. What some fear as an apocalypse, physicists dream of as discovery. The very scenario that frightens us most could also be the key to unlocking mysteries of the universe, and yet reassurance cannot erase uncertainty entirely. The story of science is filled with surprises, phenomena once dismissed as impossible, that later proved real, effects unforeseen until they appeared. The LHC itself has already pushed boundaries that once seemed unreachable. To confront the possibility of mini black holes is to confront the limits of knowledge, to acknowledge that while probabilities guide us, certainty is elusive. This duality, assurance and unease, mirrors the larger paradox of human progress. We build machines like Atlas and the LHC not because they are safe, but because they are necessary to satisfy our hunger for knowledge. And with each experiment, we wager that curiosity will not betray us. The odds are in our favor, overwhelmingly so, but the haunting question persists. What if this time is different? In the end, mini black holes may remain forever hypothetical, tantalizing possibilities that flicker at the edge of theory but never appear in reality. Or they may be glimpsed briefly, vanishing in bursts of Hawking radiation, sparks that confirm both safety and discovery. Either way, the fear they inspire tells us something profound, that science is not only about equations but about imagination, and that our greatest breakthroughs often walk hand in hand with our deepest dreads, strangelets. And the alchemy of disaster, among the catalogue of collider doomsday scenarios, none is as bizarre or as gothic as the fear of strangelets. Where mini black holes evoke cosmic predators, strangelets conjure alchemy gone wrong, the nightmare that a particle born in a laboratory could infect normal matter, spreading like a contagion until the entire Earth is transformed into a dead alien sphere. The speculation begins with the physics of strange matter. In the zoo of subatomic particles, quarks come in 6 flavors: up, down, charm, strange, top, and bottom. Ordinary matter protons and neutrons are built from up and down quarks, but theory suggests that under extreme pressures, such as those in neutron stars, quarks might rearrange themselves into more exotic states, mixing in strange quarks to form a new substance, strange matter. Unlike ordinary nuclei, strange matter could in principle be more stable than the matter that makes up our bodies, our planet, and our world. From this premise emerges the chilling hypothesis. If a lump of strange matter called a strangelay were created on Earth, it might not remain confined. It could act like a seed crystal, touching ordinary nuclei and transforming them into strange matter, one after another. What begins as a microscopic droplet could, in theory, ripple outward in a chain reaction, converting the entire Earth into a sphere of strange matter. The result would not be fiery apocalypse, but cold transfiguration. Oceans, continents, atmosphere, and life remade into a dense, featureless, strange star, shining faintly with a pale glow, utterly unrecognizable. The image is pure Gothic. Science alchemy on a planetary scale, the philosopher's stone turned executioner. On one hand, we hold the spark of curiosity, smashing particles to glimpse creation itself. In the other, we risk opening a forbidden door, unleashing a contagion not of biology but of physics. Strangelets are the nightmare of laboratory ambition. The idea that a single experiment conducted in the depths of a collider cavern could spill outward to engulf an entire planet. Physicists, of course, dismiss this fear as implausible. Calculations suggest that strange matter, if it exists at all, would not behave this way. For one, high-energy collisions tend to produce unstable states that decay rapidly, not stable, seeds capable of propagation. For another, if strangelets could convert ordinary matter, the universe would already be full of them. Cosmic rays collide with far greater energies than anything on Earth, and neutron stars are bombarded constantly. If strangelets could spread contagiously, the galaxy would already glitter with strange stars. That Earth remains intact. That ordinary matter persists is evidence that the danger is vanishingly remote, and yet the Gothic metaphor lingers, precisely because it dramatizes our unease with science at its boundaries. Strangelets are not just a speculative danger, they are a story about hubris. The alchemist's nightmare, reborn in the age of accelerators, the fear that in seeking knowledge we may stumble upon a transformation too powerful to control. It is not a coincidence that strange is the chosen name. It captures both the technical detail of quark flavor and the uncanny sense that some doors are best left unopened. This is the heart of the contrast, lab-scale experiment versus planetary collapse. On one side, we see scientists tinkering with collisions too small to light a candle. On the other, imagination magnifies those sparks into a chain reaction that consumes the Earth itself. The very disparity fuels the unease. How could something so tiny carry the fate of a planet? And yet history reminds us that scale can deceive. The nucleus of the atom is unimaginably small, and yet splitting it unleashed energies that reshape geopolitics and scarred landscapes. What is dismissed as negligible may, under the right conditions, prove catastrophic. For most scientists, this cautionary resonance is the real value of the strangelet hypothesis, not as a likely event, but as a reminder that boundaries matter. The story of Strangeles echoes the ancient warnings against forbidden knowledge, the Gothic tales of Faust and Frankenstein, the myth of Icarus flying too close to the sun. It forces us to ask not only what can we discover, but what should we risk discovering. It casts science as a moral as well as intellectual enterprise, one that must grapple with consequences as much as equations. The metaphor deepens when we consider the imagery of infection. Strangelets transform matter not through explosion, but through contact, spreading silently, inexorably. The nightmare is not destruction but assimilation, a mirror of humanity's own anxieties about contagion, conformity, and loss of identity. To imagine the Earth becoming a strange star is to imagine ourselves erased not violently, but through an alchemy that leaves no trace of what we were. And yet, for all its dread, the strangelet fear reveals something profound about human imagination. The very act of conjuring such scenarios testifies to our awareness that knowledge is never neutral, that to touch the fundamental building blocks of reality is to gamble with stakes we barely comprehend. Strangelets may not be real, but the Questions they embody about the limits of science, the ethics of risk, and the fragility of existence remain urgent. Thus, strangeles endure less as scientific probability than as cultural symbols. They dramatize the Gothic underside of the scientific project, the suspicion that curiosity may outpace wisdom, that laboratories may become crucibles of unintended disaster. They remind us that the boundary between wonder and dread is razor-thin, that every cathedral of knowledge casts a shadow of nightmare, and yet we must also recognize the reassurance science offers. The Strangelet scenario is implausible, unsupported by evidence, contradicted by cosmic precedent. It is, in the eyes of most physicists, little more than an imaginative ghost haunting the corridors of speculation but offering no real threat. The Earth has weathered collisions of unimaginable violence for billions of years without succumbing to strange matter contagion. The probability is not just low, it is infinitesimal. This is the paradox of strangelets, scientifically dismissible, yet culturally unforgettable. They linger not because they are likely, but because they reveal how deeply we fear the consequences of tampering with nature's foundations. They show us that even in the age of particle colliders, we remain heirs to the myths of forbidden alchemy, still haunted by the possibility that some transformations cannot be undone. The silence of oversight. Who decides the risks? Every collision at the Large Hadron Collider carries a whisper of risk, however small. But behind those collisions lies a deeper and more haunting question, not what the risks are, but who decides them? Who calculates the odds of catastrophe? Who certifies them safe? And who carries the burden if the unimaginable happens? The official answer is reassuring. When the LHC prepared to switch on, CERN commissioned multiple safety reviews, detailed reports authored by expert panels of physicists. These studies examined worst-case scenarios, vacuum decay, mini black holes, strangelets. Each was analyzed, tested against theory, compared with cosmic precedents. The conclusion was unanimous: the risks were negligible, far less than dangers. Nature already confronts us with daily cosmic rays smashing into Earth with energies far exceeding those in the LHC have not destroyed the planet. Therefore, human-made collisions are safe. Case closed. But critics argue the case is not so simple. Safety reviews, they note, were written by the very community that built the collider, the same scientists with careers and reputations tied to its success. Even if their analyses are rigorous, can they be truly unbiased? When billions of dollars and decades of effort converge on a single machine, the incentive to declare it safe is overwhelming. What institution would ever conclude after such investment that the risks were too high? To skeptics, the oversight is not silence by accident, but silence by design. This tension reveals a profound paradox: scientific self-policing. In most fields, external regulators exist to enforce safety on aircraft certified by aviation authorities, medicines tested by independent agencies. But who regulates the frontiers of physics when the experiments themselves probe realms beyond? Precedent? No authority exists with the expertise to judge. The only people qualified to evaluate the risks are the very ones conducting them. The guardians of truth become judges in their own trial. To many, this is reasonable. No one else has the knowledge to weigh quantum fields or cosmic rays. To others, it is unsettling. The stakes here are not localized hazards, but existential ones. A malfunctioning reactor can devastate a region. A hypothetical vacuum collapse could erase the entire cosmos. Should decisions of such magnitude rest in the hands of a small circle of experts, however brilliant, however well-intentioned? The cinematic framing sharpens guardians of truth versus gamblers with existence. The same scientists who peer into the fabric of reality become the arbiters of whether that peering is safe. Their confidence inspires awe. They trust equations enough to stake not only their careers but the planet. Yet, to the skeptical eye, the same confidence looks like recklessness, the arrogance of gamblers betting chips that belong to all humanity. Consider the lawsuits, that attempted to block the LHC's operation. In 2008, complaints were filed in European courts and even in Hawaii, arguing that CERN's experiments posed unacceptable dangers. Judges dismissed them, citing the overwhelming consensus of experts. But the cases illuminated something striking. Ordinary citizens felt excluded from decisions that might affect their survival. The courtroom became a stage for clashing worldviews, scientists wielding probability, critics wielding fear, the public caught in between. This disconnect is not new. In 1945, the Manhattan Project tested the first atomic bomb in the New Mexican desert. Some physicists privately calculated the possibility that the explosion might ignite the atmosphere. The probability was deemed negligible. The test went forward. The atmosphere did not ignite, but the calculation was never zero. That precedent hangs like a shadow over every frontier experiment since. Humanity has rolled dice with existence before. Defenders of the LHC emphasize the difference. Collider energies are tiny compared to natural cosmic rays. The Earth, bombarded for billions of years, provides a natural laboratory far larger and older than any man-made machine. If catastrophe were possible, it would have already occurred. This reasoning is elegant, persuasive, even comforting. But its critics point out a blind spot. What if human experiments probe conditions that cosmic rays cannot replicate, not because of energy, but because of configuration? A collider focuses beams, achieving densities and symmetries that nature does not. To dismiss the possibility entirely is to assume that nature has already tested every scenario. But what if it hasn't? At heart, the debate is not only about physics, but about governance. Who has the authority to weigh risks that cannot be tested beforehand? Who speaks for the billions who never consented to the gamble? Should such decisions be made by panels of experts, by governments, or by humanity as a whole? And if humanity as a whole is too fractured, too divided, then the responsibility falls by default to those with the tools in their hands. This silence of oversight is less conspiracy than inevitability. The frontier of knowledge is lonely. Few can walk its path. The deeper the physics, the smaller the circle of people able to judge it. And yet, the broader the consequences, the more universal the stake. The paradox is unavoidable. The fewer who can understand, the more who are affected. For the scientists within CERN, this is not hubris, but necessity. They see themselves not as gamblers, but as guardians of truth, entrusted with expanding humanity's horizon. They argue that to halt inquiry out of fear would be to betray the very spirit of science. Knowledge itself is humanity's shield against catastrophe. Ignorance, not curiosity, is the greater danger. They see the risks as calculated, bounded, constrained by cosmic precedent. The gamble, in their view, is no gamble at all. But critics remain unconvinced. To them, even an infinitesimal probability of cosmic disaster is unacceptable if the reward is knowledge alone. They frame the pursuit of high-energy physics as thrill-seeking, with stakes no one has the right to wager. The scientists, they argue, have become gamblers with existence, rolling dice not with their own lives but with all lives. The truth, as always, lies in tension. Science cannot advance without risk. But risks at this scale demand not only equations, but philosophy, not only probabilities, but ethics. The silence of oversight is not an accident to be corrected. It is a mirror showing us the limits of governance when knowledge itself is the frontier. Perhaps the real oversight is not silence, but trust. A trust that the guardians of truth will act with humility, that their self-policing will be tempered by awareness of what is at stake. Or perhaps it is a gamble, one we have already taken, one we will continue to take as long as curiosity drives us. For the collider hums, the detectors watch, and the universe continues to reveal itself. One collision at a time, echoes of the past. When science, terrified, the world, history, does not whisper. Here it echoes. Every time humanity has peered into the unknown with tools powerful enough to alter existence, it has faced the same chilling uncertainty. What if this changes everything? Not in theory, but in survival. The fears surrounding modern colliders are not unique. They belong to a lineage of moments when science's march forward was accompanied by tremors of dread. The most haunting precedent is the Manhattan Project. In 1942, a handful of physicists gathered in secrecy to design the first atomic bomb. Alongside the calculations of chain reactions in uranium and plutonium came a darker speculation. What if the detonation of such a device ignited the Earth's atmosphere? The idea was improbable but not dismissed out of hand. Edward Teller, the project's enigmatic figure, raised the concern, and Oppenheimer himself ordered the possibilities studied. Physicists Hans Bethe and others eventually concluded that atmospheric ignition was impossible, their mathematics showing that nitrogen and oxygen could not sustain such runaway fusion under terrestrial conditions. Yet the very fact the question was asked, and that the bomb test proceeded before absolute certainty, casts a long shadow. On July 16, 1945, as the first atomic fireball rose over the New Mexican desert, some in attendance truly did not know whether the atmosphere would burn. The world's most terrifying gamble was taken, and it succeeded. The sky remained intact. Humanity, however, was forever changed. That test was not only a milestone in physics, but a birth cry of existential terror. Hiroshima and Nagasaki followed, searing into history the truth that science's breakthroughs can double as civilization's nightmares. Nuclear physics was no longer a discipline of discovery. It was an industry of annihilation. Humanity lived. Thereafter, under the shadow of its own invention, proof that knowledge and terror are inseparable twins. The Cold War deepened this lesson. For decades, these superpowers stood poised on the brink of mutually assured destruction, their arsenals capable of erasing humanity many times over. Entire generations grew up with the knowledge that civilization could end in 30 minutes, the time it would take missiles to cross oceans. Nuclear brinkmanship was not only geopolitics but a psychological condition, embedding in culture the dread that progress had tethered humanity to a hair trigger. Scientific milestones continued to arrive during this period: the discovery of DNA's double helix, the exploration of space, the mapping of the cosmic microwave background. Yet each triumph was shadowed by the knowledge that the most consequential scientific tool of the era was also its most terrifying. The contrast could not have been sharper. The same physics that revealed the nucleus as life's foundation also enabled its weaponization. The parallels to today's frontier physics are clear. Just as the Manhattan Project carried whispers of atmospheric ignition, so colliders are haunted by whispers of vacuum decay, strangelets, or mini black holes. Just as nuclear brinkmanship forced humanity to live under a sword of Damocles, so high-energy physics forces us to confront risks measured not in cities but in worlds. Each case underscores the same pattern. Humanity pushes boundaries before certainty is guaranteed, trusting calculations, probabilities, and precedent to carry us through. This is not recklessness, but inevitability. Science cannot prove safety with absolute finality. It can only calculate probabilities. The Manhattan Project scientists did not know with certainty that the sky would not ignite. They reasoned it was vanishingly unlikely, then lit the fuse. The Cold War leaders did not know with certainty that deterrence would hold. They reasoned that a balance of terror would restrain conflict, then built arsenals. And today, physicists do not know with certainty that the Higgs vacuum is stable, or that exotic matter will not arise. They reason from theory and cosmic rays, then power up the collider. This cycle is what makes history's echoes so potent. They remind us that the march of knowledge is inseparable from gambles, that every milestone comes with shadows. To split the atom was to gamble with ignition. To orbit satellites was to gamble with militarization. To map the genome was to gamble with ethical dilemmas of identity and manipulation. Each gamble has enriched humanity, but each has also seeded new terrors. The contrast framing is stark. Scientific milestones versus existential terror. The Manhattan Project gave birth to nuclear energy and nuclear annihilation. Cold War physics gave us satellites and ICBMs, weather forecasting and doomsday clocks. Today's collider physics gives us the Higgs boson and speculative risks of cosmic collapse. The pattern is undeniable. Progress and peril are braided together, each inseparable from the other. Yet history also teaches resilience. The world did not burn in 1945, though it might have. The Cold War did not end in annihilation, though it could have. These echoes remind us that while terror accompanies progress, so too does survival, adaptation, and growth. The very fact we are here to contemplate today's risks is testimony that humanity, however narrowly, has endured its gambles. This endurance does not absolve us of caution. If anything, it deepens our responsibility. Each time science has terrified the world, it has also forced reflection on ethics, on governance, on the responsibilities of those who wield knowledge. The nuclear age birthed arms control treaties, watchdog organizations, and philosophical debates about just war and existential risk. The collider age, in its own way, forces similar reckonings about oversight, trust, and the role of imagination in shaping public fear. Perhaps that is the real lesson of these echoes, not that science should stop, but that science must always remember the shadows it casts. Fear is not the enemy of discovery. It is the partner that keeps ambition tethered to humility. The dread that haunted Los Alamos, the terror that haunted Cold War leaders, the unease that haunts CERN, all are reminders that knowledge is never free from consequence, and so the echoes roll forward. When Atlas captures collisions deep underground, it carries not only the hopes of discovery, but the weight of history. The fireball of Trinity, the mushroom clouds over Japan, the tension of nuclear brinkmanship are all ghostly witnesses, reminders that science can terrify even as it illuminates. The line between revelation and ruin has always been thin, and it always will be. The cosmic perspective. Nature already plays dice. For all the dread conjured by vacuum decay, strangelets, or mini-black holes, physicists have a simple counter-argument. An argument at once profoundly reassuring and faintly unsettling. They point to the sky. For billions of years, Earth has been bombarded by cosmic rays, subatomic particles accelerated to unimaginable speeds by violent astrophysical engines, exploding supernovae, pulsars whipping magnetic fields into storms, quasars blazing at the hearts of galaxies. These particles strike our atmosphere with energies far exceeding anything produced at the Large Hadron Collider. If high-energy collisions could trigger catastrophe, the reasoning goes, the universe would already have destroyed us. Nature itself has run the experiment countless times across eons, and we are still here. On the surface, the argument is elegant. It transforms the cosmos into a laboratory larger than anything humans could build. A single cosmic ray proton can carry the energy of a well-thrown baseball, focused into an infinitesimal particle. When it smashes into Earth's atmosphere, it collides with nuclei at energies dwarfing those of the LHC. These ultra-high energy cosmic rays are not rare. Billions strike Earth every second, scattering cascades of secondary particles that rain down invisibly. If such collisions were capable of triggering a chain reaction vacuum collapse, strangelet contagion, runaway black holes, the Earth, indeed, the universe itself would have succumbed long ago. This is the cosmic perspective. Nature has already rolled the dice at higher stakes than we can imagine, and the continued existence of stars, planets, and life is proof that the dice are loaded in our favor. Where humans fret over equations, the cosmos shrugs. Collisions happen constantly, without consequence. Yet reassurance is not the same as certainty. The cinematic tension arises in the question, is "it hasn't happened yet" truly comforting? Absence of catastrophe is not a guarantee of safety. It is, at best, an inference. The universe is vast, and while Earth has endured, can we be sure that somewhere else, sometime else, catastrophe has not struck? Might entire regions of space-time have vanished in bubbles of vacuum decay, erased too quickly to leave witnesses? The silence of survival does not prove that silence has always held. The distinction sharpens the contrast: natural experiments versus human control. Cosmic rays are accidents, scattered by the chaos of astrophysical furnaces. They strike randomly, without focus, without intent. Human colliders, by contrast, are deliberate. We orchestrate collisions at precise energies, focused beams smashing head-on with engineered densities. The geometry is different, the configuration unique. To critics, this is the fissure in the reassurance. Perhaps nature has not replicated precisely what we now attempt. Perhaps cosmic rays are similar but not identical, and in the gap between similarity and identity lies danger. Physicists acknowledge this distinction but counter that the principles remain sound. A high-energy collision is a high-energy collision. The details of geometry do not erase the fundamental physics. If catastrophe required only the energy scales achieved at the LHC, it would have been triggered by cosmic rays billions of times over. To imagine that humanity has uniquely conjured disaster through beam alignment is, in their view, to underestimate nature's profligacy. The cosmos has had infinite opportunities to test the boundaries. Our machine is but a candle in a storm, already ablaze. Still, unease lingers. The cosmic perspective is logical, but it is also rhetorical, a narrative meant to soothe. Its persuasive power lies less in mathematics than in scale. Billions of years, countless collisions, unbroken survival. But for the anxious mind, the counter-question remains irresistible. What if survival itself is an anomaly? What if we are here precisely because catastrophe has not yet happened? Probability, after all, does not forbid rare events. It merely buries them in deep time. That the Earth exists now does not mean it will always endure. The dice may yet roll against us. This tension is not just scientific but existential. We want the cosmos to serve as our guarantor, to reassure us that nature has already tested every peril. Yet the cosmos is indifferent. Its dice rolls are blind, its experiments uncontrolled. Cosmic rays cannot be cross-examined, their outcomes neatly catalogued. They give us survival as evidence, but they do not give us certainty. Human control, by contrast, demands accountability. When we switch on a collider, we take ownership of the role. Nature may have already played the game, but in choosing to play ourselves, we declare responsibility for the outcome. This distinction marks the psychological divide. Cosmic rays reassure us that disaster is unlikely, but human colliders force us to confront the reality that reassurance is not certainty and that the gamble is now ours. The cosmic perspective gives comfort. The human perspective gives dread. The two together create a cinematic tension at the core of modern physics. The sky says we are safe, but the machine in the cavern still hums with unease. History amplifies this tension. In the Manhattan Project, physicists also argued that natural cosmic rays had already tested nuclear chain reactions countless times in stars, proving safety. They were correct, but the calculation was not dismissed until after it was tested. The gamble was taken, not erased. The same reasoning appears now, echoing across decades. If nature has not burned the sky, we are safe to ignite our sparks. Yet, history reminds us that safety arguments, however logical, never entirely silence the dread. The contrast framing is unavoidable. On one side, natural experiments are chaotic, uncontrolled, vast, indifferent. On the other, human control is precise, deliberate, accountable. Nature's dice rolls ask nothing of us. Our dice rolls ask everything because we are the ones who chose to cast them. Cosmic reassurance is impersonal. Human fear is deeply personal. And yet this very tension reveals something profound. The fact that humanity debates these risks, that critics challenge safety reports, that courts hear lawsuits, is a sign not of recklessness but of awareness. We are not blind gamblers. We are creatures who seek reassurance even from the stars, who measure probabilities against cosmic precedent, who balance curiosity with fear. The cosmic perspective does not silence dread, but it reminds us that dread is not destiny. Perhaps the lesson lies in humility. Nature has already run experiments far beyond our reach. We are latecomers, apprentices at the cosmic table, our machines. are sparks compared to the lightning of quasars, whispers compared to the thunder of supernovae. To fear our experiments is natural, but to recognize that the cosmos itself has endured its own collisions is to place our fears in perspective. Still, perspective is not absolution. The dice will always roll. Nature plays endlessly, heedless of outcome. We, by contrast, must choose when to roll and how to live with the results. The cosmic perspective tells us survival is likely. The human perspective tells us survival is never guaranteed. Between these truths lies the paradox of progress, reassured by the stars, unsettled by ourselves, driven forward by the irresistible need to know. Speculative horizons beyond the known. Physics, every frontier eventually fades into fog. The farther science pushes into the unknown, the harder it becomes to distinguish between rigorous possibility and unmoored speculation. Yet it is precisely in this borderland that awe and unease sharpen. If vacuum decay and mini black holes haunt us because they rest within the equations we trust, then beyond those equations lie darker, stranger possibilities, hidden dimensions, distortions of time, instabilities we have not yet named. The universe may be far stranger than the tidy symmetries of the standard models suggest. One speculative horizon lies in the idea of extra dimensions. String theory, a leading candidate for unifying gravity with quantum mechanics, requires not 4, but 10 or 11 dimensions of space-time. If such dimensions exist, they may be curled up, invisible to us, hidden in scales smaller than atoms. Colliders could, in principle, tear momentary holes in these hidden fabrics, allowing particles, or even energy itself, to leak away. Most models predict harmless signatures like missing energy in detectors, but speculation takes the idea further. What if those dimensions are not empty but unstable? What if disturbing them awakens dynamics alien to our reality? Another horizon lies in the distortion of time itself. Einstein's relativity teaches that gravity bends time, and extreme conditions like black holes can stretch moments into eternities. But what if high-energy collisions create tiny regions where time behaves unpredictably? A bubble of distorted chronology expanding outward could fracture causality, trapping regions of space in paradox. To imagine this is to flirt with cosmic horror, a laboratory experiment spawning not an explosion, but a prison of twisted time where cause and effect unravel. No physicist predicts such an outcome, but neither can we dismiss the possibility of phenomena beyond prediction. Then there are the unknown instabilities, the dangers we cannot name because our equations have not yet revealed them. In 1895, one predicted that X-rays would pour from a cathode ray tube. In 1938, no one foresaw that splitting uranium would unleash energies to destroy cities. What then might lurk in the collisions of the 21st century? The possibility that something wholly unforeseen could emerge, something neither theory nor precedent anticipates, is itself a specter. Speculative horizons are not only about what we fear within current theory, but about the terror of what lies outside it. This is where science brushes against cosmic horror, not horror in the supernatural sense, but horror born of scale and ignorance. The abyss beyond our equations is not empty. It may contain truths so alien that our categories, space, time, matter, causality, disintegrate before them. The rational mind seeks comfort in probabilities and models, but speculation whispers, what if our models are blind? What if the abyss is deeper than we can measure and we are already peering too far? The contrast framing is sharp. Rational frontiers versus speculative abysses. On one side, physicists chart probabilities, refine equations, and test theories against data. On the other, imagination conjures abysses where reason falters, where human ambition collides with forces indifferent to logic. The frontier is rational, meticulous, cautious, precise, but just beyond its line waits the abyss, unfathomable, vast, and terrifying. And yet speculation is not mere fear-mongering. It is part of the scientific imagination, the act of asking not only what is probable but what is possible. By entertaining strange horizons, physicists stretch the boundaries of inquiry. Could hidden dimensions explain dark matter? Could time distortions illuminate quantum gravity? Could unknown instabilities hint at physics beyond the standard model? These are not only nightmares but opportunities, glimpses of truths waiting to be uncovered. The abyss is not only terror, it is also potential. Still, awe and unease cannot be untangled. The same hidden dimension that could solve cosmic mysteries could also harbor risks we cannot yet compute. The same time distortion that reveals quantum gravity could fracture causality. The same unknown instability that unlocks progress could trigger disaster. To peer into the speculative horizon is to feel both wonder and dread, exhilaration and fear. Culturally, this ambiguity resonates deeply. It echoes the Gothic tradition of forbidden knowledge, the horror of doors best left unopened. Yet it also embodies the spirit of exploration, the refusal to let mystery remain mystery. Speculative horizons blur science with myth, physics with parable. They remind us that the universe is not obligated to be safe, that progress is always shadowed by peril. The cosmic perspective provides some reassurance. Nature has been running experiments at scales far beyond ours for billions of years, but speculative horizons remind us that nature's dice rolls are not exhaustive. There may be phenomena triggered only under the precise conditions we create, thresholds never crossed until human hands constructed the right key. We are apprentices tinkering with locks whose doors we cannot yet see. So what are we to make of these horizons? Perhaps they are less predictions than mirrors, reflecting our own ambivalence about knowledge. Rational frontiers reassure us that discovery is progress, that equations guide us safely. Speculative abysses remind us that curiosity can summon dread, that ambition always risks overreach. Together they form the true landscape of science, a terrain where awe and unease are inseparable, where each step forward into the fog may reveal wonders or horrors or both. The existential mirror, why we tempt the unknown. Why do we do it? Why again and again does humanity court the unknown, even when the unknown carries the whisper of annihilation? The question is not merely technical, it is existential. To build colliders that could, in the darkest fears, unmake the world is not only an act of science but of identity. In our pursuit of the frontier, we reveal not only what we know, but who we are. The story begins deep in the past, long before equations or laboratories. When the first humans tamed fire, it was both salvation and threat. Fire cooked food, warded off predators and warmed the night. Yet it also burned forests, destroyed villages and scarred flesh. To wield it was to gamble, and yet they did. They could not resist the glow of the flame, the promise of mastery. Knowledge was salvation, but always tinged with doom. Centuries later, civilizations turned their gaze upward, learning to chart the stars. Navigation by starlight opened oceans, linked continents, birthed trade, and spread ideas. Yet it also brought conquest, plagues, and the collapse of cultures unprepared for the encounters it enabled. To map the sky was to expand horizons and also to unleash terrors across Earth. Knowledge again was double-edged, expansion and ruin, promise and peril. The cycle continued with the atom. When physicists split uranium in the 20th century, they unlocked a new epoch. Nuclear fission became energy, promising limitless power, but it also became bombs, flattening cities in fireballs of unimaginable heat. To split the atom was to split destiny itself, dividing humanity into a species capable of survival on planetary scales and of self-destruction on the same. And then came the stars again, this time not as guides but as destinations. Rockets lifted us beyond Earth, giving us photographs of our fragile blue world suspended in black infinity. Spaceflight became a triumph of engineering and imagination, yet it was also born of missiles, of Cold War arsenals designed to annihilate. Our reach for the stars was inseparable from our flirtation with Armageddon. Knowledge, again, was salvation, shadowed by doom. The collider is simply the latest mirror in this long chain. To smash particles at nearly the speed of light To glimpse forces that shape the universe itself is to continue the same human pattern, to touch fire, atoms, and stars. We are heirs to every civilization that dared before us, inheritors of their courage and their hubris. We tempt the unknown because it is what we have always done. To refuse would be to deny ourselves. But why? Is it curiosity, the deep hunger to understand? Perhaps the child who asks why 1,000 times becomes the scientist who builds machines to ask it anew. Curiosity is not a luxury but a compulsion wired into us as survival. To know is to adapt. To understand is to endure. Yet curiosity alone cannot explain why we risk so much, why we gamble with forces that might undo us. Is it hubris? The arrogance of believing we can control what we barely grasp? Perhaps. History is filled with stories of overreach, towers built to touch the heavens, myths of Icarus and Prometheus, warnings against the pride of mortals. The collider in this light is not merely curiosity but audacity, the refusal to accept limits, the insistence that even the laws of nature must yield to human will. Hubris drives progress but also ruins. Or is it destiny? Perhaps our gamble with existence is not reckless but inevitable. To be human is to push boundaries, to reach beyond safety. Each civilization has left traces of this impulse. Cave paintings, pyramids, telescopes, accelerators. Perhaps we cannot help ourselves. Perhaps our role in the cosmos is precisely this, to ask questions so dangerous they risk everything, because only through such risks can understanding grow. If so, the collider is not an aberration but a culmination of a symbol of what it means to be human. Here lies the existential mirror. Each of these motives, curiosity, hubris, destiny, reflects not only what we do but what we are. To tempt the unknown is to define ourselves against it. The risks we take are not separate from our identity. They are its expression. We are a species willing to gamble everything for knowledge because knowledge itself is our salvation and our potential doom. The contrast framing sharpens this truth. On one side, knowledge as salvation, fire illuminating the cave, navigation guiding the lost, fission powering cities, colliders unlocking mysteries. Knowledge as the force that rescues us from ignorance, that saves us from stagnation, that ensures our survival against chaos. On the other side, knowledge as doom, fire consuming villages, navigation spreading conquest, fission obliterating cities, colliders sparking apocalyptic fears. Knowledge as the force that tempts destruction, that summons the very dangers it claims to master. This duality is not weakness but essence. Salvation and doom are twins, inseparable in the pursuit of understanding. To walk the path of knowledge is to carry both. The collider does not break this pattern, it exemplifies it. Humanity builds machines that might unmake the earth, not because it seeks doom, but because it seeks truth, and truth has always carried danger. Perhaps this is the ultimate paradox. The very thing that makes us human, our thirst to know, is also the thing that could undo us. Yet to renounce it would be a greater doom still, a surrender to ignorance, a betrayal of the very fire that carried us from caves to colliders. We tempt the unknown not because we are reckless, but because to be human is to choose wonder over fear, even when wonder comes with risk. In this light, the collider becomes less a machine than a mirror. It shows us not only quarks and bosons, but ourselves, a species balanced on the edge between salvation and doom, forever gambling, forever reaching, forever questioning. And in its hum, in its sparks, in its collisions, we hear the echo of every ancestor who dared before. They touched fire, atoms, and stars. We touch the universe itself. A future we cannot rewind. There is no rewind button. That is the final, sobering truth at the heart of every risk we have traced, from vacuum decay to strangelets, from black holes to unknown instabilities. If we are wrong, we will not know until it is too late. No alarms, no last-minute switch to flip, No heroes sprinting to halt the countdown. The cosmos does not grant retrees. A mistake at these scales is absolute, woven instantly into the fabric of reality itself, and yet the pursuit continues. Why? Because to be human is to open doors, even when the rooms beyond are dark. Forbidden knowledge has always called to us, from the firelight of prehistory to the roaring hum of colliders buried beneath mountain. We tell ourselves the risks are calculated, the probabilities infinitesimal, the safeguards certain. But beneath those assurances lies something deeper, an inability to resist the unknown. It is not only science that drives us, but compulsion. Curiosity is the thread stitched through our history, and to sever it would be to unmake ourselves. Still, the final warning cannot be ignored. The universe is not obligated to indulge us. It does not bend probabilities for our comfort. If the Higgs field is metastable, if strange matter is contagious, if hidden dimensions are fragile, then a single spark could be enough. The chain reaction would not care about our intent. The equations, once violated, would not ask forgiveness. There is no undo. This is the paradox that defines our age: hopeful progress versus irreversible risk. On one side, the dream that colliders and theories will deliver new laws of nature, answers to dark matter, glimpses of quantum gravity. I hope that knowledge will be our salvation, illuminating paths to energy, medicine, and survival among the stars. On the other hand, the nightmare of curiosity could collapse the floor beneath us, ending not only humanity but the story of reality as we know it. The scales are asymmetrical. Salvation adds wonders, but catastrophe erases everything. And yet, to halt would be unthinkable. Imagine if our ancestors had refused fire, fearing burns. Imagine if sailors had shunned the ocean, fearing storms. Imagine if physicists had refused to split the atom, fearing destruction. In every case, fear was warranted, and yet the leap was taken, and history changed. To deny the leap is to remain in darkness. To take it is to risk illumination or oblivion. The choice, it seems, is never really a choice at all. So the collider hums, protons race, detectors watch, equations stretch, and humanity waits not in fear alone, but in awe, perched on the knife edge of knowledge. Perhaps we are safe, protected by laws we do not yet understand. Guardians written into the universe itself, perhaps Hawking's chronology protection, or cosmic censorship, or some deeper principle ensures that our gambles cannot topple reality. But perhaps not. Perhaps nature allows the dice to fall wherever they may, and we are merely the next throw. The final warning, then, is not meant to paralyze, but to awaken. It reminds us that knowledge is not neutral. Every experiment is also a wager, every discovery a reflection of our character. We are not only scientists and engineers, but gamblers of destiny, choosing to cast dice whose stakes no one fully comprehends. The awe lies in our courage, the unease lies in our blindness. Both are true, and both define us. When audiences leave the story, they should feel what physicists feel in their deepest moments, that the universe is both fragile and vast, terrifying and beautiful, that we are tiny sparks daring to illuminate infinities, that the risks we take are as real as the stars above us, yet so too is the wonder that compels us forward. And so the closing image is this: a door half open, light spilling from a room we cannot see. We know the dangers, we feel the dread, yet we reach for the handle anyway because we cannot do otherwise. The future waits on the other side, irreversible and unknown. Perhaps it will be salvation, perhaps doom. Most likely it will be both. There is no rewind button, only forward.
Only the next experiment, only the next collision, only the mystery we cannot resist.